as Joe mentioned in the beginning, one of the problems that visually impaired face is running into things, which is why we developed the collision avoidance system. If you suppose we have an object that is, well, currently out of the range of the user. We utilize a ultrasonic sensor which emits a high frequency sound wave on the front of the cart. The range, 5 feet currently, is not sensing anything. But once the object is in range, it'll send a rumble to the left-hand side of the handlebar, indicating the object is near. As a user approaches, the intensity grows. Similarly, if the user approaches the right-hand side, meaning they're about to collide with the shelf, a right-hand side rumbler vibrates, indicating an impending collision. These systems operate only when the cart is moving, and Kevin will explain how we determine that.
Alright, so as we introduced in the beginning of the presentation, we're going to install a Hall effect sensor near the wheel region of our cart. As you can see by the animation, we have 2 magnets of opposite polarity attached to the wheel, and the Hall effect sensor embedded underneath the wheel well. And what happens is, as you can see, a change in polarity across this device will result in a change in output from the device. And this is nice because it's already in digital format of 1 or 0. You can put this directly into the microcontroller. Now, why do we need this? Number one, we can tell how far the cart has traversed. Given 1 wheel rotation, which is 1 period of the square wave, we can measure the circumference of the wheel and output that back to the server to update the location of the cart. In addition, as Andre stated, we want to know when the cart is stationary, when it's been still for a given period of time. When the cart is still, you don't want the RFID system to be pulsing out constant reads, as this is extremely power inefficient. And similarly, you don't want the rumblers to be going off if the cart has been still for any given period of time, as this would be the constant user. Now to go over in more detail the flow of the design is a little.
Now that you know a little bit about how the product works, I'm going to take you through a functional flow in terms of the actual hardware that we're using. First, when the cart is moving, as you already have seen, the Hall effect sensor will send a signal to the microcontroller. When the cart is moving, the microcontroller will send a read command to the RFID reader. As Kevin said, we only want to make a read when the cart is moving to save power. The reader will then scan and return the ID of the nearest RFID tag and return to the microcontroller. The microcontroller takes this information and relays it through a ZigBee radio unit to the backend server for processing. The second function is when a user would like to input a destination to be routed to. First step, push the talk button, sends a signal to the microcontroller saying that the user would like to input a destination. Again, it passes it through the ZigBee to the server, letting it know that the user would like to input a destination. At this point, the server opens the audio channel between the wireless headset and itself, and it receives the input and it recognizes the voice of the user. After computing the route, it will speak to the user and let the user know which direction to go, left or right or straight, to reach their destination.
For the backend server will gather all the information that the shopping cart has sensed, and it will make an informed decision on how to get to the destination. We set up a database in this backend server to store all of the RFID tag information. So we have a virtual map of the store. This makes the software very scalable. So for different grocery store layouts, we can just adjust the database tags. Now, in addition to the database, we also included a graphical user interface. The reason for this is that in the event that the shopper needs help on an aisle, they can push the talk button and say help or assistance, and we'll be notified on the graphical user interface that this user needs help in this aisle and this section on the aisle. Now, this could be implemented on a monitor by the cashier's box or in the manager's office, so that way they can send help to this user. So when the OK button is pressed on this message box, a message is sent to the shopper on the headset, and it'll say help is on the way. So that way the shopper knows that they're getting help. Now, Vinci will go over the testing and verification methods we had in the system.
For the testing and verification of our product, we tested it based on different functionalities. one of the functionality for the accuracy of the RFID reader. We want to make sure that it was able to read at reliable ranges, at a good amount of distance, and at different locations, as well as the tags being mounted on different materials, such as a wall or a shelf or metal. Afterward, we tested the wireless communication replacement module, which communicates from the cart to the back-end server. We tested to make sure that it works well indoors at a long distance. And then we tested the accuracy of the navigation system with the voice recognition, as well as generating the routes and the directions that it provided to the user. And lastly, we tested the collision avoidance system with the ultrasonics and the objects in front, making sure that the rumbles go off as we approach an object in front, as well as along the wall or something on the side. And then after we completed all the testing of the functionalities, we implemented all the components together and did a final verification, making sure that all of them work together. So now Joe will go over the hardware design of our system.
Yes, all the components we talked to you about have to go somewhere, and we decided to put them on printed circuit boards. Because of the development and the things being developed independent of each other, we have 2 circuit boards so that should anything go wrong with one, we can replace half of the system instead of replacing the entire system. The first circuit board, is the primary board. It's the RFID communication board. It supports the RFID reader, the primary microcontroller, the wire replacement radio, as well as the Hall effect sensor. The secondary board, which will be used for the sensor feedback, will support the secondary microcontroller, our ultrasonic sensors, as well as our DualShock vibration motors. Both boards do this through a series of voltage regulators, peanut capacitors, diodes to protect in case of vacuum flow currents, as well as in one case transistors. Now, how much does all of this cost? Long story short is it costs about $1,150 for us. We were able to save money through cooperating with Team Wedge Watchers as well as using our own computers. I'd like to draw your attention to how much the M10 model costs as well as our RFID tags. So when we go into production, the thing that drops down the least is our SkyTech model. But the thing that drops down the most is our RFID tags. We paid about $100 for 50, but you can buy them in bulk for $20,000, and each bulk for 20,000 tags. And if you do the division, it comes out to about $154 for 1,000 tags. So if you put that in one store, retrofitting the first cart will cost about $750. But retrofitting the second one will cost only about $600. Keep in mind that most stores only want 1 or 2 carts, and at most, if they have a high volume of visually impaired customers, they probably want at most 5. To go over the development more in depth, we have Tatsani.
To efficiently utilize our human resource, we have broken down our project into subsystems. The engineers who work on the subsystem are as follows. On the navigation system, David and myself. On the RFID system, it's Winty and Alan. And on the collision avoidance system are Kevin and Andres. And on the hardware part, it's Joseph. Next is our milestones. Most of our milestones are delayed up to 10 days. Here are the actual milestones that we achieved. On November 14th, haptic feedback and ultrasonic sensor functional. On November 23rd, navigation software developed. And on November 24th, RFID reader interface. And lastly, on November 28th, testing and finalization began. Into closing, here's Joe.
So what